Okay, so now we are in 4.2, which we're now going to start looking at log functions. Here are our objectives. All right, so let's start. The definition of a log function. So for x greater than 0 and b greater than 0, so x has to be positive and b has to be positive, where b is not equal to 1, y equals the log of b, the log base b of x is equivalent to b to the y power equal x. So let me explain some lingo that I use. This b right here, well, this is the base of the log. And x, well, that's the argument of the log. And then y is the value that we get from doing that log. So what they're saying is that's equivalent to doing the base raised to the value will equal the argument. So base raised to the value will equal the argument, where again b is the base and x is the argument. Here are some examples. So we have 3 equals log base 7 of x. And what we're going to do is write that in equivalent exponential form, which means we need to pull out, well, what's the value, what's the base, and what's the argument. Well, the value is 3, the base is 7, and the argument is x. So then remember, the equivalent exponential form is base raised to the value, so you raise it up, equals the argument, which means you'll end up with 7 raised to the third power equals x. Here are some more examples. Again, it's base raised to the value equals the argument. So b to the second power equals 25. Log base 4 of 26 equals y. The equivalent form would be 4 to the y power equals 26. Base to the value equals the argument. Okay, so since we can go from log to exponential, we can also go from exponential to log. So this time they give us base raised to the value equals the argument. And we have to write it in the log form, which means it's going to be log base of the argument equals the value. So this turns into log base 2, because that was the base. The argument was the x, so log base 2 of x equals 5, which was the value. Another one, so b to the third power equals 27. Well, b would be the base. 3 would be the value. And the 27, well, that's our argument. If you follow the same form, that's how they'll all be set up. So b is the base, 3 is the value, and 27 is the argument. So if you write it in log form, it's going to be log base b of 27 equals 3. And then one more, e to the y power equals 33. Well, e, that stands for Euler's number, so you think of it as an e, it's an actual value. So this time e is going to be the base, y is the value, and 33 is the argument, which means your equivalent log form should be log base e of 33 equals y. Okay, so here's some more properties of our logs. If we have log base b of b raised to the x power, so this time they're saying the argument and the base are equal. So when your argument and your base are equal, In essence, they cancel out, and this time you're just left with that exponential, which in this case is x. So when your base and your argument are equal, they cancel out, so that's the log, and you're left with just the exponent, which in this case was x. And here's another one. If we have b raised to the log base b of x, again, because it's raised, they have the same base, they cancel out, and you're left with just x. These are equal. They cancel out, and you're left with just x. Okay, another one, log base b of b equals 1. So this is just like before, when the base and the argument are equal. The log cancels out along with the base and the argument. And then what's the exponent that's up here? It's a 1. And that's why you're left with 1. And then log base b of 1, doesn't matter what the base is, for any base, log base b of 1 is going to equal 0. So if it was log base 2 of 1, that would be 0. If it was log base 10 of 1, that's also 0. Okay, regardless of what the base is, if it's log base b of 1, it equals 0. If it's log base b of b, that equals 1. Because remember, if your base and your arguments are equal, the log basically cancels out, and you're left with this exponent, which in this case is a 1. All right, let's go in our books to page 465. We're going to start by looking at number 5. And it says, write each equation in its equivalent exponential form. So this time we have 5 equals log base b of 32. And they want us to write this in the equivalent exponential form. So let me remind you that the log is written as log base of the argument equals the value. Okay? So what you're going to do is pull off the pieces from the problem they gave you. So the base is a 6. Okay, that's b, my fault. My b's and 6's look the same. The base is a b. The argument, well, the argument is 32. It's the thing you're taking the log of. It looks horrible. There we go. And the value, the thing that is equal to, is 5. So you got the base is b, your argument is 32, and your value is 5. So now we're going to write the equivalent exponential form, and the equivalent exponential form is base raised to the value equals the argument. Base raised to the value equals the argument. So in this case, we're going to have b raised to the 5th power equals 32. So b raised to the 5th power equals 32. All right, let's look at number 7. So number 7. It says log base 6 of 216 equals y. So again, the base is 6. The argument is 216, and the value is equal to y. So you should come up with 6 to the y power equals 216. Let me block some of this off to make some room. All right, let's look at number 13. So number 13, now it says write each equation in an equivalent log form. So they're going to give you the exponential form, and you must write it as a log form. So number 13 says the cube root of 8 equals 2. Yeah, that's actually true. We believe that. So what we first need to do is rewrite this. So you have this base, which is 8, raised to a power. Right now it's in a cube root. So I'm going to write it as 8 raised to the 1/3 power equals 2. Let me remind you that if you have a root, like a square root or a cube root, let's just use this example. The number on the outside, so example, I have a 3 out here. The number on the outside, which is the a, goes on the bottom of the fraction. So now I'm looking at the exponential, and the exponential will be a fraction. The number on the outside goes on the bottom. The number on the inside goes on the top. And the thing that you're taking the root of, he becomes your base. So this is x to the b over a power. This was 8 to the, well, what's on the inside? A 1. So 1 over 3 power equals 2. Okay, so now we see that the base is equal to 8. Go back to this definition. The value, well, that's 1/3. And the argument, that's 2. All we're doing is writing each piece as we see it. We're placed basically as a matching game, isn't it? Once you have the matching game ready, you're going to put the pieces back into this form. So now that says log base 8 of 2 equals 1/3. And then last one, number 19. And it says 7 to the y power equals 200. So again, let's pull off our information. The base is 7. The value is y. And the argument is 200. So you should come up with log, because remember you need to write the log because you're going into log form. Log base 7 of 200 equals y. Okay, let's move forward. Oh, actually, let's continue practicing problems. Look at that. All right, let's go look at page 466. We got 4 more problems to look at. We're going to start by looking at number 21. So the previous slide, we were working on going from log to exponential and from exponential to log. Now we're going to practice on evaluating these logs without actually using a calculator. So it says evaluate each expression without a calculator. Number 21 starts us off with log base 4 of 16. Now, even if you wanted to use a calculator, you couldn't, because your calculator works in log base e and log base 10. This is base 4. So what we're going to do is we're going to write this. We're going to rewrite this, and we're going to try to use the properties we learned before. So let me remind you of one. Log base b of b raised to the x power. So remember when the base and the argument were equal, they canceled out along with the log, and you were left with just that exponent? Well, your goal here is to make your make your argument be the same as your base. You can't change your base, but you can rewrite your argument. So this becomes log base 4 of 4 squared. What I did was just rewrite the 16. And 16, I can rewrite it using a 4, right? It's 4 squared. So now the base and the argument, they're equal. So they cancel out. And you're left with just the exponent, which was a 2. All right, let's look at number 29. So we have log base 7 of the square root of 7. So again, we see our base and our argument are equal, but there's no exponent up here. You have to have an exponent, which means you need to rewrite the square root. So following what we did on the previous slide, when you rewrite a square root, the power should become a half. The number on the inside is a 1. The number on the outside was the square root, so it's a 2. So this is saying log base 7 of 7 to the half power. Since the base and the argument are the same, these cancel out, and I'm left with just that exponent, which is a half. All right, number 31. So now it says log base 2 of 1 over the square root of 2. Okay, so first thing we need to do is rewrite the square root. So let us rewrite the square root. So you have log base 2 of 1 over 2 raised to the 1/2 power. I'm going to put this in parentheses so I can separate it. What I just put in parentheses, that is your argument. And your base here is a 2. Now, even though I see the base and this 2 are equal, it needs to be in your numerator. So what we're going to do is we're going to move this 2 to the 1/2 power, take it from the denominator, and move it into the numerator. So to do that, you leave the 2 alone, and you change the sign of the exponent, so now it becomes negative a half. Now your base and your argument, they're equal, cancels out, and you're left with just the exponent, which was negative a half. And then one more, let's look at number 33. This time we have log base 64 of 8. Now I know I can write 64 as 8 squared, but you cannot change your base. You can only change your argument. So think, how can you write the 8 so that it's a 64? How are they related? So this is log base 64 of the square root of 64. Isn't the square root of 64 8? Therefore you rewrote it without actually changing it. So now the base and the argument are the same, but you need an exponent up here. So you need to rewrite the square root. So this is log base 64 of 64 raised to the 1/2 power. The base and the argument are the same. These cancel out. You're left with just the exponent, which was a half. Okay, so now graphing exponential and log functions. If I had the function f of x equals 3 to the x power and g of x equals log base 3 of x, what you want to do is graph them in the same coordinate system. So the first thing you're going to do is graph f of x equals 3 to the x power. This exponential form and this log form, they are equivalent. So the first thing you're going to do is graph f of x equals 3 to the x power. And remember, all we do is pick some x values, plug them into our function, and we get our y values. So we have the point -2 1/9, -1 1/3, 0 1, and 1, 3. Now, in order for you to graph the log base 3 of x, once you have these points, all you're going to do is reverse the coordinates. The x becomes the y, and the y becomes the x. So if you have to graph a log, and it's not a base 10 or base e, you start by graphing the exponential form, and then you reverse the x and y to get the log form. So the 1/9, now this point has become 1/9, comma, -2. This one has become 1/3, comma, -1. This is 1, comma, 0. And this is 3, comma, 1. Plot these points, as well as these points, since we're graphing them in the same plane. The red graph is 3 to the x power, that's the exponential. And then the blue is log base 3 of x. And notice that they are inverses, I'm sorry. Yes, they're inverses of each other, and they're symmetric about the line y equals x. So it's basically a mirror image. Okay, so if you have to graph a log and it's any base other than 10, where you cannot use your calculator, you start by graphing the exponential form, reverse the x and y, and then plot them in the same plane together. All right, so here are some characteristics of the log functions. First thing, the domain of the log function. So if I have f of x equals log base b of x, well, the domain is going to consist of only positive real numbers. So 0 to infinity, do not include the 0. You cannot take the log of 0. The range consists of all real numbers. So you can expect to get everything back out, but you can only put positive numbers into your argument. The graph of all log functions passes through the point 1, 0. Because remember, the log of 1, doesn't matter what the base is, will always be 0. The x-intercept is 1, obviously, because it goes through the point 1, 0. And there is no y-intercept. If it's in this form, or actually I'll say this form up here, it'll never touch the y-axis, therefore there is no y-intercept. I'll leave characteristics 3 and 4 for you to read through. Let's look at 5. So the graph of f of x equals log base b of x. It approaches but does not touch the y-axis. Okay, therefore the y-axis, or the line x equals 0, is a vertical asymptote. You remember your exponential functions had a horizontal asymptote, and it was the line y equals 0. But now your log function has a vertical asymptote, and it's the line x equals 0. Characteristics 1, 2, and 5 are the ones you need to know, and then 3 or 4 is just added information. Let's talk more about the domain. I'm going to let you read through this. The part I'm going to stress on is the last sentence. It says the domain of the domain of a function that's log base b of g of x consists of all x for which g of x is greater than 0. So this is telling you that your argument has to be greater than 0. So if you were finding your domain, the first thing you want to do is set the argument greater than 0, and then you want to solve for x, and then give your solution or your answer as an interval, and possibly graph it on a number line. Let's go to page 466. We're going to look at number 75. And it says find the domain of each log function. So we have f of x equals log base 5 of x plus 4. So we need to find the domain, which means we need to be looking at the argument. The argument is the thing you're taking the log of. So this is, I literally say log base 5 of, and then that piece that follows the of, that's your argument. So this x plus 4, that's our argument. So we need to go ahead and set it greater than 0. That's step 1. Set the argument greater than 0. And then step 2 is to obviously solve for x. So x is going to be greater than negative 4. Now I'm going to put this on a number line. So we have negative 4 on our number line. It says greater than negative 4, so we know we're going to use the parentheses because we're not including it. And it's going to face the right because we're greater than. And then shade. put an arrow. And then I like writing the infinity off to the right, off to the side, so I'll know it's there. So then when you give your interval answer, the interval would be -4, comma, infinity. So any x's you pull from this interval and you plug in here, they will work. Any outside this interval will make your argument negative or 0, which you cannot do. All right, let's look at number 79. So we have f of x equals the natural log of x minus 2 whole thing squared. Now the natural log is just like log. Natural log is really just log base e. So we're still looking for domain, which means we're still focusing on the argument. So the argument is all of this. The whole x minus 2 whole thing squared. And you want to set that greater than 0, right? Which means, let's think about it this way. If it's squared on the outside, this is always going to be positive. It's this entire thing, which means that x minus 2 has to be greater than 0. Okay, let's say that again. Let's go backwards for a second. I like how I said it the first time. X minus 2 whole thing squared, because of this squared, so this is a square, which means this piece, all of this, will always be positive. So you don't have to worry about it ever being negative. What you need to be concerned is, can it ever be 0? So in that case, we're going to do x minus 2 cannot equal 0. Normally you would say greater than 0, and that would take care of the not equal to. But this time, this will always be positive. So what you need is say, I hope, or you don't want it to be 0. So x minus 2 cannot equal 0, which means x cannot equal 2. Draw a number line. Put 2 on the number line. Now, because it's a not equal, we know we open a parentheses to the left and a parentheses to the right, and then we shade. And don't forget your arrows. So when you write out this interval, you have negative infinity, comma 2, union 2 to infinity. So you're saying it can be anything. Anything will work except for 2. So let's pick a number from this interval. How about 0? If we put it back into the natural log, so we have the natural log of 0 minus 2 whole thing squared. Well, that's the natural log of negative 2 squared, which is the natural log of 4. The argument's positive, so we know that's valid. And if we pick a number from this interval like 3, now we have the natural log of 3 minus 2 whole thing squared. And that's just the natural log of 1 squared, which is the natural log of 1, which is totally valid because, again, 1's positive. The only thing that will not work is x equal to 2. If you plug the 2 in here, you'll have the natural log of 2 minus 2 whole thing squared, which is the natural log of 0. And that you can't do. All right, so common logs. Base 10 is known as the common log function. It's the base that your calculator works in. So when you hit log in your calculator, it automatically does log base 10. Here are some properties. We went through property 1, log base b of 1. Doesn't matter what the base is, will be 0. We looked at property 2, 3, and 4. Now for the common logs, base 10, it still holds true. So log of 1 is 0. This is as a base 10. The base doesn't matter. If the argument's 1, it's 0. Log of 10, know that the base is 10. Remember, when the base and the argument are equal, these cancel out, and you're left with that exponent, which in this case is a 1. Same thing here. When it's an invisible base, it is base 10. they cancel out because they're equal, the base and the argument, and you're left with the exponent, which is x. And the same here, the base and the thing you're raising it to, that 10, they're equal, which means they cancel out, and now you're left with the argument, which is just x. Same properties, this time, instead of base b, it's base 10. Base e, if you have a log base e, that's the natural log function. That's why we call it the natural log. And you write it in the form ln, which stands for the natural log. You can also write it as log base e, but you'll have to remember to put the e there. If you write log of x, we assume you mean log base 10 of x. If you want the e, it's better off to go ahead and write natural log. That means log base e. And of course, we have properties for the natural log, just like we have for the common log and any base log. So natural log of 1, that's also 0. The natural log of e, well, in this case, let's work this one out. Natural log is the same as saying log base e, and then you have an argument of e. Well, when the base and the argument, they're equal, these cancel out, and you're left with that exponent, which is 1. And that's why the natural log of e is 1. The natural log of e to the x, by the same concept, is just x. And e raised to the natural log of x is just x. E and natural log, they are inverses, so they cancel each other out. All right, let's go in our books again on page 466. We're going to look at numbers 81 first. So let's look at number 81. And it says evaluate or simplify each expression without using a calculator. So no calculators. And we have log of 100. Well, the base is invisible, which means it has to be base 10. So this is really saying log base 10 of 100. We want to use the property where the base and the argument are equal. So we need to rewrite 100, so it's written as a 10. So that's the same as saying log base 10 of 10 squared. Your base and your argument are equal, so this disappears, and you're only left with the exponent, which is a 2. And number 85, it says 10 raised to the log of 33. So again, we have an invisible base, which means he is base 10. So this is 10 raised to the log base 10 of 33. These are equal, so remember this cancels out along with the log, and we're left with the 33. Number 91 has the natural log of 1 over e raised to the 6th power. So the first thing we need to do, we need the argument to be in our numerator just like before. So that e to the 6th power, he needs to come up, which means now we have the natural log of e to the negative 6th power. When you move from the denominator to the numerator, you leave the e alone, and the 6 becomes a negative. And then the natural log and e, they're inverses, so they cancel each other out, and you're left with just the negative 6. All right, one more. Let's look at number 95. So it says natural log of e raised to the 9x power. Well, again, e and natural log, they're inverses, so they cancel each other out, and you're left with the exponent, which is 9x. Okay, so this will conclude our video for 4.2. Please email me if you have any questions.